In this video, I will present Data Parallel C++ and talk about how it extends the SYCL standard with new features for enhanced productivity and performance. My name is James Brodman, and I work as a software engineer at Intel. I would like to thank my co-authors, Michael Kinsner, Ben Ashbaugh, Jeff Hammond, Alexey, John Pennycook, Jason Sewall, and Roland Schulz. I would also like to thank all of my coworkers at Intel who have contributed to this effort. The outline of this presentation is as follows. First, we will quickly explain what is Data Parallel C++, or DPC++, and its relationship to the SYCL standard. Next, we will cover a few of the extensions defined in DPC++. These include unified shared memory, unnamed kernel lambdas, in-order queues, subgroups, reductions, and other simplifications. Finally, we'll have a brief summary and tell you where you can get started with DPC++. The simplest way to think of DPC++ is expressed by a simple equation. DPC++ equals modern C++ combined with the SYCL standard from the Kronos group, and then a set of extensions added on top of that strong foundation. The extensions DPC++ provides have two goals. The first is to enhance productivity for programmers. Simple things should be simple to express. We don't want long, complicated incantations of syntax to get between the programmer being able to quickly and completely express their algorithms. So DPC++ tries to simplify common patterns in SYCL by reducing the verbosity that modern C++ can occasionally introduce. The second goal is to enhance performance. Getting the best performance for your applications is the goal when using any type of device. So DPC++ gives programmers the necessary control over how their programs execute so that they can squeeze every last drop of performance from their hardware. Next, we will go through several of the extensions that DPC++ has defined on top of SYCL. We will start with unified shared memory. Data management in SYCL is done through the buffer abstraction for memory objects. Buffers are very powerful and allow expressing complex data dependencies between kernels, but they do have a few drawbacks as well. Extending an existing C++ program with SYCL requires you to replace all your pointers in C++ arrays with buffers, and this can be a time-consuming and error-prone task. Unified Shared Memory, or USM, provides an alternative to buffers that is based on pointers. USM complements the buffer abstraction and is not meant to replace it. Allowing programmers to reuse existing pointer-based code simplifies getting an application running on a device. USM helps programmers do this by giving them the desired level of control over data movement while preserving the ease of use of C++ pointers. The core concept in USM is the three different types of memory allocations that it defines. The first type of allocation is a device allocation. These are allocations in device memory that are accessible on the device, but not on the host. Programmers must explicitly copy data between host memory and device allocations. This requires extra effort from the programmer, but allows total control over when data movement occurs and how much data is moved. The next type of allocation is a host allocation. These are allocations in host memory that are accessible both on the host and on the device. The data stays in host memory and is remotely accessed by the device, often over a bus like PCI Express. The final type of allocation is a shared allocation. These are allocations that are accessible both on the host and on the device that can migrate between host memory and device memory. Data is automatically moved between host and device by lower-level runtimes and hardware. USM provides several flavors of APIs to allocate and deallocate the three types of USM allocations. Next, we will go over an example comparing how buffers and USM are used in a program. Here, we have a simple vector add kernel that adds together the elements of two arrays and stores the results into a third array. First, we must allocate our C++ arrays on the host. This is done using standard malloc. Next, we initialize arrays A and B on the host with some values. Now we can declare buffer objects that will represent our C++ arrays. We create 3 buffers and initialize each with its respective array A, B, or C. After our buffers have been created, we begin launching our kernel. First, we must declare accessors for each buffer. We declare 2 read-only accessors for our inputs and a write accessor for our output. After we create our accessors, we define our kernel by calling parallel for on the handler. The kernel reads from our input accessors and writes the sum to the output. Finally, we wait for the kernel to complete. After it is finished, our buffers exit scope and bring the output back to the host, updating our original C array. Now, we will show how this example can be written using USM shared allocations. First, we must allocate our arrays. Here, we do this using a templated form of malloc shared that will allocate n integers against the device and context used by the SYCL queue. After that, since USM shared allocations are accessible on both the host and device, we can directly initialize the input arrays, A and B, on the host since they're regular C++ pointers. After we have initialized our inputs, we launch our kernel. Since we are using USM pointers instead of buffers, we do not need to create any accessor objects inside the command group object. Instead, we can directly read from our pointers to A and B and write to array C. Finally, we wait for our kernel to finish executing. After it is finished, we can then proceed to read the results of our addition in array C on the host. The programmer does not have to specify any data movement. Simply reading array C on the host will bring the memory to where it is being used. SYCL programs using buffers order the execution of kernels through data dependencies specified by accessors. These data dependencies allow programmers to define complex execution graphs that the runtime executes in a legal order. With USM, we no longer declare accessors when defining kernels. Consequently, USM cannot use data dependencies to order the execution of kernels. Instead, we must use an alternative method to define how kernels are ordered in a program. Luckily, SYCL already defines an event mechanism. Whenever a kernel is submitted to a queue, the submission returns an event. These events can be used in several ways. First, programmers can explicitly order kernels by manually waiting on events. However, this can be cumbersome for programs with many kernels and complex dependencies between them. DPC++ adds a new method to specify kernel dependencies in the form of the depends on method in the handler class. Depends on takes an event or vector of events and informs the runtime that the kernel being submitted cannot execute until all the specified events have completed. This mechanism preserves the ability to specify complex execution graphs that SYCL can express. Summarizing, unified shared memory makes it easier to get applications running on an accelerator. Data movement can either be explicitly controlled by the programmer or implicitly managed by the system. USM shared allocations and their implicit data movement make it very easy to integrate into existing C++ applications, allowing reuse of code that operates on pointers and arrays without modification. For more information on other uses of USM, I encourage you to check out the IWOCL presentation from Michal from Intel on using USM and OpenCL. That presentation is titled, Taking Memory Management to the Next Level, Unified Shared Memory in Action. In it, he compares the programming models of USM and OpenCL shared virtual memory. Moving on, the next data parallel C++ extension we will discuss simplifies how kernels are written in SYCL. SYCL 121 requires all kernels to have a unique name. When writing a kernel as a C++ lambda, this name is expressed as a template argument to parallel 4. However, there are cases where it can be difficult to come up with a unique name. In most cases, this name is never even used by the programmer. DPC++ allows programmers to omit this name when using its compiler to generate code for both the host and the device. On the right, we revisit our vector add example. Here, we specify the name vadd for our kernel as a template argument to the parallel 4 call. In DPC++, we can omit this name, simplifying the code. The next extension concerns queues. SYCL queues are out of order by default. This gives the runtime maximum flexibility when executing graphs of kernels with complex dependencies. However, this complexity is more than many applications require. It is a very common pattern to have a linear chain of kernel executions where each kernel executes after the previous one has completed. DPC++ adds the ability to create queues that have this in-order semantic. On the right, we have an example where we submit 3 kernels, where each kernel depends on the previous one. The dependencies are expressed using another feature introduced with USM that allows programmers to specify dependencies using events through the new depends_on function in the handler. If we write this example using DPC++ in-order queues, the code becomes simpler. Previously, the programmer had to manually express the linear dependence pattern. With this extension, this dependence pattern is implicitly expressed through the in-order semantics of the queue. This reduces both work for the programmer and the chance of introducing an error by forgetting to specify a dependence. The next extension introduces a new level of the hierarchy to ND ranges. Subgroups represent an implementation-defined subset of work items in a workgroup that execute together. Examples of this include SIMD units on CPUs and warps on NVIDIA GPUs or wavefronts on AMD GPUs. Understanding which work items execute together allows developers to reason about how work items will be scheduled, which can be important for performance tuning and correctness. Here, we have an example where we are using subgroups to improve the performance of accumulating a value across multiple work items. There are a few things to note in this example. First, an instance of the subgroup class is required to access underlying subgroup functionality. This can be obtained from the ND item. Next, the attribute required subgroup size, applied here to the kernel lambda, can be used to request a specific subgroup size. This can be done for different reasons, such as matching the hardware's native SIMD width, or tuning to relieve register pressure. Finally, subgroup functions like all of and reduce enable communication across work items in a subgroup, mapping to efficient instruction sequences. The next DPC++ extension adds a common pattern in parallel programming to SYCL. We saw a very limited form of this pattern in the previous extension on subgroups. Kernels that perform reductions combine multiple values to produce a single output. This is an important pattern in many different application domains. Reductions have simple semantics. First, the input values can be combined in any order. Next, only the final result is meaningful. It could be a sum, maximum, or some other operation. Implementing efficient reductions is very challenging. DPC++ shifts the burden from the programmer to the compiler and runtime. In this example, we use a reduction to compute a dot product of two arrays, A and B. The reduction operation is described by a few things. First, you must define a reduction variable. In this example, it is called sum and will store the result of the dot product. Next, we must specify how we want to combine values. Here, values will be added together using the plus templated operator. The kernel lambda must also take an extra argument, a reducer variable for each work item. In this example, we call it partial sum and use it to accumulate the partial results of the dot product. The implementation will then combine the reducers and store the final result in the reduction variable sum before the kernel completes. Note that a kernel can accept any number of reduction objects. The final extension is really several smaller features that we're grouping together under the umbrella of simplifications. Simple things should be simple to express. Towards that end, we've introduced Class Template Argument Deduction Guides, or CTAD, for many SYCL objects that simplify their declarations in code. In the snippet below, we can use CTAD to simplify the declaration of a buffer. First, we can infer that we are creating a two-dimensional range from the fact that we're initializing it with two values. Next, we can infer that we want a two-dimensional buffer from the two-dimensional range. Finally, we can infer that it should be a buffer of integers because pointer has type int star. We've also defined several shortcuts on the Q class that allow expressing kernels using parallel for directly on the Q object. This saves the programmer from having to write a potentially empty lambda. There are other simple enhancements that aren't covered here, and we have several more planned. This has been a brief overview of just a few of the extensions that DPC++ defines. In conclusion, Data Parallel C++ builds on the foundation for heterogeneous programming in C++ provided by SYCL. The extensions we've defined build on SYCL with new features that improve both productivity and performance. All of these features are being developed through our open source implementation of DPC++ on GitHub, and the link is provided below. Feel free to check out DPC++, leave feedback, or even file a pull request. Additionally, specifications for these extensions and more can be found either at the GitHub page or at oneapi.com. Thank you.